Make sure that it's there.
The content of this meeting is being sent to one or more apps.
Okay. All right, let's go. YouTube. Where's my YouTube link? Okay. Make
I'm
sure
impressed.
it's there. Okay. It should be.
Yay.
I think I hear my goofy voice, so it should be there.
We are
Yeah,
live.
Yep, there we are. Okay. All right, let's see who. I usually give it well, we'll give it a few minutes because I know last week, I think Les or Margaret said something that it took like a couple minutes for it to um send in the notification.
yeah,
So we'll just chit chat a little bit.
yeah.
Let it stew.
Let it breathe.
Yeah, let it breathe. See what pops in.
The wrong hand gesture, but whatever.
Yeah, it's all good.
Yeah.
But yeah, this is exciting. We always like having you on because it's fun.
No, like don't expect too much. I'm like a basket case just now. So
I just think it's funny like how many times we've tried to make this work.
no, and half of it's me because I'm kind of like I'm the world's worst procrastinator, right? So
Yeah.
my brain is like turning on crap all the time, but it's like, yeah, it's reprioritizing all the time.
Yeah.
It's like an old Windows PC. Yeah, the IRQ is always at 1, never at 11, right?
Yeah. Right.
Like, yeah, so it's always fallen to the bottom of the list. It's like my inbox. Do I want to answer that? Maybe not. Okay.
Yeah. Like, is that really that important? I don't know. No.
Yeah.
To the bottom. To
No,
the bottom you
no,
go.
generally I love doing these things.
Yeah.
So it's just, and I have too many kids.
Yeah. That
So,
that can take up some other time too. So
well, they tend to throw curveballs,
yeah.
especially at the
Yes.
weekend. So,
Right. They have things to do. Things to do, you know?
my stuff is definitely not a priority. It's like they just roll their eyes.
Yeah. Like
So,
what? You want to
yeah,
do
what this is space crap.
yeah, like why? What's so great about that?
Yeah, I don't know. Who gives a shit about that big boring yellow thing in the sky?
Yeah.
You know,
That boring thing.
In Scotland, it's like a theoretical object anyway. So,
Right. Yeah, I've heard many things
yeah.
about it. Like yeah, it's like perpetual cloud cover all the time.
Yeah, I remember the one and only time I ever saw the aurora from Scotland. When
Yeah.
I was driving back from Aberdeen to Glasgow, and it was like maybe 1 or 2 in the morning.
Okay.
And I looked in my rearview mirror, and all of a sudden it just lit up.
Yeah, it's like, whoa.
I was driving over a moor and descending from a moor up the Rannoch Moor, way up top end of Loch Lomond,
Uh-huh.
and I was descending down, and my rearview mirror just lit up with magenta, and I was like, "Holy
Yeah,
shit!"
it's like, holy crap.
So that was pretty cool. That was my first ever time seeing them with the naked eye.
That's
I've
neat. Yeah, it's always a good like that when you get to see it like that, it's always memorable. So
Well, now, of course, I try to go back and figure out what day that was. I know it was in February. I know it was like minus 10 degrees,
uh
freaking cold, winter.
yeah.
And I was trying to figure out what year it was. I couldn't even remember what year it was. I'll go, oh, I could go look at what event that was because that
Yeah.
was, but yeah, I guess even to see them in the north of Scotland's not that special.
Mhm.
So,
That's pretty neat. All right. Let's see. See if anybody's there. I guess we could probably start it. But yeah.
so is
So
it
anyway,
Viking hat or not Viking hat?
that's hilarious. I
I
like
could,
how you kind of blurred out the horns.
no, but yeah, like,
There you go.
yeah.
I
I got
don't know why I don't know why
all
he's
I
taking the
moved all my
this background.
paraphernalia into my office space, and then I'm like, I've got shit all over the place. Um,
All right. Well, we'll get this started. So welcome in everybody. We finally got Dr. Scott McIntosh on again. We've been trying to schedule this for a couple months now, and then things pop up and things get shuffled around. So yes, F.
it's an F bomb.
Yeah, F. It's an F. Okay, that's funny. F bomb. I need one of
Sorry,
those.
I totally threw you off your stride there.
No, you're fine. So we're here. We're back. We're gonna talk sun stuff with the master about the sun. So I'm looking forward to this. maybe we'll get hints as to what's coming, or maybe what's coming. I don't know. He's always throwing in some interesting things. So that's why we like having him on here, and he's highly entertaining.
Hold on, I'll
And
go get a beer from the beer fridge is just right here, by the
yeah,
way.
so it could get more and more entertaining as it goes on.
Yeah.
But we're giving the Starlink a try because in case you haven't noticed, there's a woods behind me, so I'm in the middle of nowhere in the Upper Peninsula. So yeah, but Starlink hasn't failed me yet, knock on wood. So hopefully this will work just fine. So without further ado, I will pass it on over to Scott, and we'll talk about the state of the sun, which I'm super happy we are seeing it right now. It's been 3 days since I've seen it, so
That's because you're nocturnal.
yes, nocturnal, true.
You're nocturnal.
Yeah, nocturnal.
Yeah.
All right, so I will pass it on to you.
All right, let's see if I can see if this works again. Worked
Yeah,
last time.
we did test it, so hopefully there we
All
go.
right. Are you good?
I see it. I see it.
All right, so I'm hoping that my Wi-Fi stays up because it's been getting kind of choppy the last few days. So I've got to turn my screen brightness down, otherwise I look like I'm bleached. Okay.
It's like
All right.
lighting.
It's a bit intense. I know. All right. So like I'm just going to preface this, but this is it's a talk I put together when in 2014 actually. I gave this at the European Space Weather Week in 2014. Allegedly I won a bottle of whiskey for this talk, right? But this isn't the talk as it was, but it's what I've done is I've kind of taken that and based on conversations I've had with Tanya over the last couple of months
Uh-huh.
and with you all guys and some of this mysterious stuff that's going on, I've kind of spliced in some updates and stuff. But it's kind of curious, right? It's like
Yeah.
kind of how looking at how the system works together, right? And like the fact there's all this bullshit about how cycles and seasons, so we call them seasons, I call them seasons and storms. So things that happen on a decadal scale, things that happen on a yearly scale, and things that happen on a daily, weekly, monthly scale, right?
Okay.
And it's all part of the one machine,
Yeah,
not different machines. It's all one machine.
right.
And so this is an effort or it was a circa 2014 effort to try and stitch everything together, right?
Okay.
But do it in a way that people that haven't seen a lot of this work can kind of get it. All right.
That makes sense. Yeah.
So I've updated it in places, and the hint will be in the bottom right-hand corner. So down here, there'll be there a 2014 or a 2025.
Okay.
So, all right. So let's kick this thing off, right? So everybody's probably seen this plot before,
Hmm.
right? So this is Dave Hathaway's, I guess. This one's from 2013, so it's a relic, right?
It's a yes.
It's a relic. It's a part of the historical record now. So the idea, of course, is that you get butterfly, you look at the sun and you map out the locations of the sunspots, you get a butterfly diagram because take your head, you get a big like a butterfly on its side. Exactly,
Hi.
right? And of course, if you integrate through the butterfly, you get the sunspot number. And so the whole idea here is these are cycles, right? So it's a really crude proxy for solar variability and decadal scales, right? So we've kind of got to the point now where we're kind of right. The thing that's underlying this is the really important part, right?
Got it.
Right. We'll get to that in a minute. But this is just a preface. But I'm talking about a definition of a season, right? So
Hmm.
you've probably heard us talk about this a little bit, but the sun goes through episodic surges. You've seen them,
Yeah.
right? Yeah, where you all of a sudden it'll go and and activity will increase, significantly over 6 months, and then over another 6 months it'll wane again.
Yeah.
And so this is actually the number of C class flares
Okay.
since what, 1975-ish? So
Yeah.
you
It
can
looks
see very spiky, right? And it's Also northern and southern hemisphere. So it's red and blue, red north, blue south. You can see that there's massive excursions in the number of flares, right?
Yeah.
This is not random, right? This is part of the thing, is like so much of this is not random at this scale. Now, at the scale we go to next, it gets random,
Okay.
right? Okay, so big organization, Sunspots, huge organization, 20, decadal scale. Then inside the decadal scale, you get there's something going on that makes spots on a shorter time scale, but it collects them in clumps.
Okay.
And then inside of the clump, the challenge is, okay, once you've got a clump, when's it going to flare, right? So that's when you get into the storm event. And so here's the first flip, right? So people think that this is us somehow finagling data and that there's something magical about this. And actually the periodicity is about 11 months, believe it or not. So
Okay.
if you analyze the period of all these bumps and wiggles, it's about 11 months, not 12.
Yeah.
11, but this was completely ignored in the literature, right?
Interesting.
Completely.
That is interesting.
That's fascinating, right?
Yeah.
We could do a whole talk on why.
Okay.
But here's an update, right? So I made this one last year because what I was trying to do was trying to recalibrate. On our Discord, there's a whole conversation about calibration of frickin' GOES data, right?
Yeah.
And
Yeah.
so I'm trying to understand whether the massive disparity between cycle 23 and 24, because it really jumps down
Hmm.
in terms of flare output, is real. You can see that the pulsing remains, but the amplitude drops. And there's still some weird there was some weird calibration issues. Interestingly enough, in the bottom plot there, so if you can make that out, it's the butterfly diagram from flares.
From flares. Okay.
Yeah. So green is C,
Okay.
yellow is M, and red is X.
Huh.
Right? So you can see if you just focus here at 2017, you see the X-class flares in 2017. See them?
Yeah.
Southern hemisphere close to the equator. So by the end of the talk, we'll go, why the fuck are those things happening near the equator, near solar minimum? That's a question you've got to ask, right?
Yeah.
Remember that question. I want it
Okay.
verbatim, like that, right? What? Bert? Anyway, because it turns out that there's always a last great flare in a
Okay.
cycle, right? And that's not my phrase, that's someone else's phrase. So if you look at times of like solar minimum, look at 1985, there's 3x flares.
Yeah, you're right. Okay.
96, 97, there's a couple.
Hmm.
2006, there's the ones in December right after Hinode and Stereo launched. They kept everyone very busy through the solar minimum. Right?
Yeah.
Great. And then 2017, and of course, what will we get, right? Next
Yeah.
time. So
Right.
anyway, these are all related. And so the thing that I never get the chance to do that I won't talk about, um, we'll talk about it a wee bit later.
Okay.
And then there's storms, of course. And I love this animation, right? This is an old animation from the early days of SDO. Looking at starter cycle 24.
Okay.
And it's in the 1600 passband. And that's usually that's close to the UV continuum. But there's bright emission lines that sit in there. So when you see that like crack of lightning,
Hmm.
that's actually carbon-4 emission. So that's carbon being heated up. They're probably going
Really?
through 1 million degrees. So yeah, it's pretty cool. I like it.
That is cool.
Looks like lightning. And so of course, episodically there are large complex regions that form. They like to spew shit our direction, right?
Yes.
So the Carrington storm's a beautiful example of that. But there's so clear in how the system sets up. We'll get to that in a little bit. All right.
Okay.
You've seen this before. This one hasn't changed. I love the idea that there's a Kraken lurking below the surface, right?
Yeah. Yeah.
Usually I say there's a spherical cow underneath, but forget about that right now, right? I hadn't come up with the spherical cow in 2014. So anyway, how does the machine work that makes all this stuff? It's all end to end. It's not one process that dictates the seasonal stuff. not another process that dictates the cycle stuff and another process that dictates the storm stuff. They're all together.
Okay.
So if you can't explain them all in one concise way, you're not explaining anything. That's just me, you, and the YouTubers, right?
Yeah.
That's just my perspective. So of course, I always go back to my little friends, furry friends, the bright points, right?
Yes.
Because like a teenager is covered in spots, the sun, in their little tiny active regions, and you can see, bright pointless sun on the left, bright point identified sun on the right. So again, this is 2014, right?
Mhm.
So you've seen this, what, last year?
Yeah.
So I bet you didn't see was this cool bit, where we were actually, if I flip back and forth, we were actually long ago, we were actually trying to see the reason we got onto this, because we were trying to see if there was a hidden spatial scale,
Okay.
right? So the sun has multiple scales of convection, right? So there's granules, which are a few thousand kilometers across. There's supergranules, which are a few tens of thousands of kilometers across. And then there's this hypothesized scale, which is,
Okay.
they call it the giant scale, and it's about hundreds of megameters across. And so what we kind of identified was that the bright points like to live at the vertices of this 100 megameter scale,
Okay.
right? Which is kind of cool. So
Yeah.
you've got all these scales of circulation going on, right?
Mhm.
And they're nested one inside of the other. The difference with the giant scale is that it's directly tied to the rotation of the star,
Okay.
right? So it's not just a normal spaghetti thing where you've got convection going on in circulation. This is circulation that's driven by the heat in the atmosphere and the rotation of the atmosphere above it. So like you start to see weird shit between the low latitudes and the high latitudes and things like that.
Okay.
So if I was to tilt this on pole, if I was to rotate this round, you'd notice that inside 55 degrees, there's not much.
Okay. That magic 55 number that I remember.
That's another thing that doesn't appear in the literature very much.
Right.
Anyway, all
Yeah.
right. I love 55 degrees. And so if you build a histogram of this, you can see granules, supergranules, and then a bump. And the third bump is what the fuck, right?
Uh-huh.
So we wrote all this shit back in 2010, and we had a hell of a time convincing the referees, as always.
Right.
No, none of this has changed, right? So you were seeing that when you had these concentrations of 100 megameter flux, you get an EUV breakpoint right on top of it. And the funny thing is that these things, this is unpublished work, rotate faster than the surface,
Huh. Okay.
right? Because that we're basically implying that the magnetic field is rooted way down low in the atmosphere.
Mhm.
And because it's not at the surface, it's actually moving faster.
Okay.
And so
Yeah.
what happens is it basically very slowly tears through the atmosphere, right? So anyway, so all of this shit should be really familiar. I mean, you guys should be able to give this slide, right? So
Yeah.
top one is so this is a snapshot. So if you take that snapshot and just look down the central meridian and build it up with time, you get the thing on the top. The thing you haven't seen is the bottom thing on the bottom. We tend to not show that because it's harder to explain.
Okay.
And that is the evolution of this longer length scale, right? So there's the bright points, which are a marker of the length scale, and then we can actually go into the magnetograms and pull that length scale out. That's what you see at the bottom, right?
Okay.
And so if you think about it, you actually get a better look at this thing that we now call the extended cycle, right? So you can see if I can, no, I can't see my cursor, but you can see that the branches extend to much higher latitudes
Yeah. Yep.
and they go much further back in time. It was a warning flag, right?
Yeah.
Right?
Yep.
And
Yep.
so this is all monkeying around, right? My then 5-year-old was drawing straight lines.
Good.
Right? So this is the whole straight line challenge, right? And the
Yeah.
interesting part of this, right? So if I toggle back and forth and make everyone really dizzy, went way too far back. This is the torsional oscillation. Do you know what the torsional oscillation of the sun is?
Dare describe it for everybody.
All right, so when you're measuring the rotation of the sun, you basically on a day-to-day basis, there's a standard model for rotation,
Hmm.
right? And this thing is what you get when you take the standard model away from what we actually see,
Okay. Yeah.
right? So there's what we actually see and what the sun's actually doing, and then there's the conceptual model, right? So if you take the whole sun and assume it's a rigid, not a rigid body, but if you assume it's a rotating sphere, you would have a profile for rotation that looks like a bell curve, right?
Okay.
This is the pattern that lives on top of the bell curve,
Okay.
right? So there's a bell curve pattern, and then there's a pattern over the top of it. Guess what it looks like? It looks like our extended cycle buddy, right?
Hmm.
That's not new.
Yeah. Right.
That's not new. Nobody ever published it, but it's not new. So, these plots are all very old. You can tell because his color schemes are fucking awful. But, the thing we got to is like, this is the kind of eureka moment. And actually, the thing that helped us, believe it or not,
Yeah.
was the asymmetry,
Okay. Yeah, I can
right?
see that.
So if you look at the northern hemisphere and the southern hemisphere, you see that the bands start at very different times,
Hmm.
right? So there's actually about a 2-year separation,
Yeah, I can see that.
right? But the march towards the equator is always the same speed. So these are space time plots.
Hmm.
So any line on them is a speed,
Okay.
right? And that yellow dotted line there is, I think, 3 degrees per year,
Okay.
right? So that's the kind of average speed. And so you can train your 5-year-old to draw straight lines and clap like a seal. And then one day you're coming out, you're sitting going, holy fuck, what's that? So you've got the two hemispheric maxima. You've got these two yellow lines that that start at 55 degrees at different times. And those starting points seem to line up with the hemispheric maxima. And you're like, oh, wait a minute. What's going on? Long story. Lots of indented text.
I see.
But the whole thing is like, holy shit, this is like an interference pattern, right? So there's what the whole idea was that there's a magnetic signal line behind this,
Okay.
and there's cancellation going on. So magnetic fields always want to be zero,
Hmm.
right? So if you've got one field somewhere, there's always an opposite field to balance it out, right? That's Maxwell's first law, I think, or second law. I can't remember. Whatever, one of them,
One of
right?
those. Yeah.
And so the idea is that magnetic field always goes to zero. And so what we've got, the premise here is we've got overlapping magnetic cycles, which we now call the Hale cycle,
Hmm.
and they're playing with one another.
Okay.
Right?
Okay.
And so when they interfere, so the time of solar maximum, actually the next solar cycle is starting to appear,
Hmm.
and it's interfering with the one that's already there, which actually dials down the amplitude, right?
Interesting. Okay.
So,
Yeah.
because the other supposition we make is that when magnetic field emerges, it's because it's buoyant, and it's only buoyant because it's got less pressure than its surroundings,
Okay.
right? It's just like a cork, right, or a
Yeah.
hot air balloon, right? And so the premise is that the buoyancy is modified by how many connections that piece of magnetic field has.
Interesting. Okay.
Right? So the more connections it has, or the stronger the connections it has, the less likely it is to make spots.
Okay.
Okay, so it's just it's a buoyant thing. So it's all about pressure balance, right? So if it's in total balance, you get no spots.
Hmm.
That would be the time of solar minimum.
Makes
But the
sense.
magnetic fields are all still there. That's the
Yeah.
crazy.
That
But
is kind of,
there's no imbalance.
huh.
Okay, so there's our lovely Hale. This is all 2014. This is ancient, right?
Right.
And here's the other ancient thing, right? So you've got this thing, you draw the picture with the underlying magnetic fields behind there. You're like, okay, this starts to make sense. kinda. There's an event in here, of course, that I haven't identified yet, right? Which is the one that, what the fuck's going on in 2011,
That's right. Yeah.
right?
Yeah.
There's something going on that switches this thing, right? Well, I think I can't remember what we called it in the 2014 paper. I mean, that 2014 paper took almost 3 years to get published. So
That's quite some time.
that's a bit frustrating. But anyway, another one of the old plots that was floating around is we called this thing it's telecommunication, but teleconnection is probably a better phrase. That's what they use in meteorology to describe when like the different global scale weather systems are connecting with one another,
Okay. Yeah.
right?
Mhm.
So, and of course, magnetic fields, like I said earlier, always want to connect, right? There's always a sense of cancellation. And so all we were trying to illustrate with this crappy diagram was you've got these four, you've almost always got two magnetic systems playing with one another. There's only one time when you don't.
Hmm.
That's the ascending phase of cycles,
Okay.
right? There's only ever two bands and oppositely signed bands in each hemisphere. They are joined by a new pair at solar max. That new pair goes on to become the next sunspot cycle,
Okay. All right.
but 11 years later.
Yeah.
Okay, so just this is all bullshit. Okay, ignore it.
Ignore it.
Still old slide. Things haven't changed. Sunspot cycle appears to be a consequence of the interaction of latitudinally, temporally overlapping bands of the 22-year magnetic activity cycle. I think we can probably categorically say that's true
Hmm.
10 years later, because we basically predicted it, right? We'll talk about that in a minute. But it's an interference of mutually canceling magnetic systems. Magnetic fields are really beautiful because they always want to be zero, right? 55 degrees, nobody gives a fuck. The hemispheres are treated independently, but they're not because they're part of a larger global scale system. The bands don't always start at the same time. We see that. That's what gives rise to hemispheric asymmetry. We don't know quite why that happens. We have ideas, but
Okay.
and then the degree of overlap seems to inversely correlate with cycle strength. So this is a prelude to something that came 6 years after,
Okay.
right? So this is the connection between the extended cycle, the Hale cycle, and this upcoming cycle amplitude.
Interesting. Okay.
Okay? So it's kind of cool to go back and look at this shite.
It is. Yeah.
Yeah. So, but the system seems to be driven by rotation of the radiative zone, right? So the radiative zone lives below the convective zone. And that we think this is why you've got the problem with 55 degrees,
Okay.
right? So basically, you've got a sphere rotating under an ocean.
Yeah. Okay. Yeah, I can see that.
And the pieces that line up cylindrically with the underlying thing kind of spin as a body. Kind of, not quite.
Hmm.
But the things that the polar regions are kind of spatially, actually, they're topologically disconnected from the ones on the sides.
Yeah.
And so you get this weird thing that happens at the interface between that system and that system. And I'm not voguing,
No.
right? Right?
Oh,
But that's interesting. So you've got a system that's doing this, and then a system that's topologically disconnected from it, that's doing that slowly, but it's also doing this,
okay. Yeah. Yeah.
right? So you've got a polar cell that's turning this way, meeting a one that's going this way. What are the conditions for a dynamo again? Oh, yeah, that's right. That's when you can convert a toroidal field to a poloidal field and back again. Oh, shit.
That's right. Okay. Yep.
Fuck me. Anyway, all right. Just ignore that. Okay. So there's evidence for this tangent cylinder at 55 degrees, right? So you've got this cylindrical system. But maybe all the magic is happening between the two, right? So there's something weird going on at the poles. There's evidence that things are aligned because that's where you get giant cell convection from,
Yeah.
right? The fact that all these things line up with rotation or are driven by rotation, right? Again, if I showed you the projection of the bright point density from the pole, you'd see that there's almost nothing above 55 degrees.
Hmm.
All right. Better still, when you project these things out, and I'll show that in a second, it looks like Rossby wave patterns. So Rossby waves are giant scale planetary waves that are buoyancy-driven waves as a result of rotation. That's what we have in our atmosphere. In fact, most planetary atmospheres have them. Yeah, apparently our sun doesn't have them, if you know what I mean.
Okay. Yeah.
You know, every rotating atmosphere has these waves. You can't avoid them. The difference with the sun is that they're magnetic.
Yeah. Yeah.
Okay, so we'll get to that in a minute. So, of course, item 4 here, the ability to draw a straight line. We're into crappy chart territory, right?
Hmm.
So anyway, let's just fuck with that. So here's a flash forward. This is actually from an email I sent to the person that was in my old job, Maura Hagen, who's the old NCAR deputy director at the time. And she was looking for sound bites to send along to the NSF.
Hmm.
And so I sent her this slide and I was like, holy shit, I think we've found something interesting. And of course, you know, if you this is from 2012, if I update to the several years later, look, it's all following. So there's my scale measure at the top, bright
Yep.
point at the bottom. You can see the scale measure follows the magenta lines, and the bright points are following the yellow lines.
Yeah. Yep.
That's pretty fucking good.
I'd say.
I would say that's pretty fucking good. I've got a really
Yep.
5-year-old, right? But better still, we're saying in the paper that, well, the spots of cycle 25 should start to appear 2020-ish. Because what's going to happen? Something's going to happen at the equator, and all of a sudden everything's going to spring to life. At this point, it still doesn't have a name,
Hmm.
right? So here you go. There's the update again. So it keeps trucking in.
Yeah.
There you go. Just for shits and giggles, I'll throw the sunspot butterfly diagram on top of this thing, right? I know it's probably projecting awfully, but whatever. Anyway, I always like to take these time capsule moments, right? So I don't think that anything we've said on this longer scale is categorically wrong.
Right.
Also not saying it's categorically correct.
Like,
Right?
well, yeah.
But it's bloody interesting, and it might be a hint, especially if this relationship between all of this phasing and the amplitude holds true, right?
Hmm.
So let's look at quasi-annual variability, right? So this is the part you haven't seen, right?
All right.
So you know, at the time of writing, everybody was very concerned that over the last 3 decades, a lot of solar proxies have been tailing off, right?
Yeah.
Because if you remember 2020 timeframe, everybody was writing papers about the grand solar minimum,
Yeah, they were. They were all like, it was
right?
going to get
Oh
quieter.
my God, because everything's trending down. Climate change, right?
Yeah.
Right. And so at this time, we were looking at this and we were trying to understand the origins of it. And we'd noticed that the cosmic ray flux was doing some weird things. And we'd noticed that all the weird scales that we were looking at were weird. But on top of that, we noticed this weird quasi-annual signal in the flare and CME records, right?
Hmm.
Right. So I think what's this? This is C flare. So panel A spots. You can see it in the sunspot numbers. It's not that hard to find. B is flares. And the C class flares, if you turn them into a butterfly diagram, this is just a density plot, right? This isn't MXC. This is only C class flares. What we kind of noticed was that when more flux comes through the surface, news flash, you get more flares,
Right.
right? News flash, right? And so, we're looking at this. This again, 2014, we're looking, cycle 25 is appearing on our charts, right?
Hmm.
we're trying to understand where we are in this global scale interaction system, right? So these arrows are meant to indicate one banded system playing with another banded system, right?
Okay, yeah.
Yeah, so it's just an interaction between that thing and that thing. The one, of course, I'm missing is the one that goes across the equator, right?
Mm-hmm.
So, but there they are, right? So, but it's kind of interesting because now you've got a bit of a conundrum that'll help us in a minute, right?
Mm-hmm.
So one of the things that we're looking at here is you'll notice that when you look at the magnetic butterfly diagram, there's very regular pulses in it.
Mm-hmm.
Can you see them? See
Yeah.
these streaks that go off towards the poles?
Yep.
Well, there's some really weird shit, right? Because the common interpretation of this is that is evidence in support of the Babcock-Leighton dynamo model. Is
Okay.
that the magnetic flux that emerges at mid-latitudes gets swept at the surface and swept towards the poles. What they don't talk about is stuff like what happens in 1990. Now,
Mm-hmm.
take your eye back to 1990 and look at those white stripes. What did they
Yeah.
do when they get to 55 degrees?
Oh yeah.
They like go up and down.
Uh-huh. They're
Why are
like
they coming back down again?
yeah.
Right? So that's about the time of the big Quebec flare, right?
Okay.
Right? The field at high latitudes was really, really strong
Mm-hmm.
because that became cycle 23, right? No, it must have been 20. Yeah, that became 24, 23, 23. All right, okay. Sorry, I can't get my number right.
23.
But
Final answer.
it really puzzled us that the stuff
Yeah.
would chuck up and bounce. It's almost like it hits a wall and reflects.
Uh-huh.
So if it was going all the way to the poles, why is it reflecting?
Right. Yeah.
Anyway, don't tell anyone. All right, so if you just look at C flares and plop them on this, you can actually see a remarkable imprint of the magnetic field, right? So
Uh-huh.
you get a surge in magnetism, you get a surge in C-class flares. Look at the M-class flares, it becomes even more clustered in time,
Mm-hmm.
right? It's like there are specific longitudes where you're going to just make more longitudes. Remember that there's a dimension on the sun that nobody cares about because the sun's flat. That actually isn't flat.
You're right.
Spheres rotate. And
Mm-hmm.
so longitude, people. And then you look at the X-class flares. And they're very, 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 very certain about when they occur. Right? So if I
Yeah.
go, oh, sorry, my bad. What the hell? C's, M's, X.
Okay.
And that's what happened when you overlay them all. And I think for shits and giggles, I may have thrown B's on there, but I don't know why the hell I did that. So, but the idea here is it's like you've got this clustering process that's going on. So on top of your decadal scale pattern, there's something else that's going on, which is making it surge from
Mm-hmm.
time to time. But it's not any different from the thing that's giving you the decadal scale pattern, right? So here's
Right.
some. So this is the top one is the number of CMEs from measured by LASCO. So again, this is only 14 years. But I could update this. I haven't tried to update it. I should stop being so fucking lazy. But the CME rate modulates by 100% during one of these pulses, right? 100%,
That's crazy.
right? The
Yeah.
sunspot number, which you look at the middle panel, is between 50 and 100%.
Wow.
It's small, right? So
Yeah.
you've got decadal scale envelope, and then on top of it, you've got this other pattern going. I might be one of the only psychos that thinks about this stuff, right? Maybe not. Maybe there's other psychos out there. I can't wait to hear from you all.
Yeah.
And then the bottom one is the flare rate. And if I look at the flares, right? So north, south, this is from two different spacecraft, right? So there's RESI flares on here and there's GOES flares. And I've showed you the record that goes way back to the 70s. Well, bugger me. The rate of flares goes up by 100% too.
Yeah.
Something's driving the magnetism, right?
Uh-huh.
Just to go a layer deeper. Let's look at radiation, right? So the total solar, I was very naughty in 2014. I used to call the TSI the total solar irrelevance.
Instead of
Actually, the total solar irradiance.
right.
And the whole reason for that was because in climate world, this is the thing they point to and go, well, the sun's irrelevant because its modulation over a decade is only 1 watt per square meter or a couple, and that's not enough.
Right, yeah.
And that's probably true, but what we were looking at the time was not so much that, but what's the variance in the UV, the EUV, and the X-rays, because it affects different parts of the atmosphere. Right? So if you're worried about the thermosphere and the expansion of the thermosphere and drag on a satellite, you want to know what the UV, the EUV, and the X-rays are doing. And so if they're modulating by 50%, you got a problem,
Right, yes, you do.
right? And we've seen that in full effect, right? So if I look at the number of deorbits of satellites right now, I can correlate it to pulses of solar magnetism. Like,
I
it's
believe it.
beautiful.
Yeah.
It's really pretty. Yeah. No, if you're a satellite operator, though.
No, no.
So, so anyway, so one of the things we're doing here is just messing around with what is the wavelength dependence of these pulses. And it's kind of cool, right? So sunspot number on the left, data from Soho Virgo, and then the spectral irradiance from the Lyman alpha line up to other lines. So this is just nodography, right?
Mhm.
This is just going to the nth level just because we fucking can.
Right, yeah. Like I do it, I
And
could do it, I'm doing it.
yeah, but the idea is that all through all these wavelength ranges, you see this imprint of the same phenomenology. It's right.
Hmm.
You want to go a wee bit more psycho?
Yeah.
You you take the magnetic field itself and you start to decompose it. Right? So you try to break it into its long-term and short-term parts. I don't know why the hell I did this, right? And I could probably do it a lot better with AI now, but like the end result is the things the patterns you see at the bottom. So you've got this decadal scale pattern that we know and love ish,
Hmm.
and then sitting on top of it is this higher frequency thing, right? Which is producing all these things. But again, I'm not saying that everything goes to the pole because if you look at my diagnostic, it doesn't really look like it gets to the pole.
Right, yeah.
But that means something weird's happening at 55 degrees again, right? So it's either being subducted back down or it's being reflected or something. We don't know.
Hmm.
And I'm not sure when orbiter gets up high enough, 2028, we'll be able to tell for sure. What I think is actually is going to happen is all this shit's going to be refound again in 2028.
Right, yeah.
Oh my God. There's something weird happening at 55 degrees. Call the police. So anyway, getting into this was the bit that was kind of really strange, right? That you can throw Fourier transforms at this and try to understand what the periodicities are. And so we see, of course, there's a 28-day, 30-day period, right?
Hmm.
We knew that one, but the odd one was this peak that's back here at 330 days or 11 months,
Yeah.
right? And everyone, oh, it was epic, right? It's tidal. It's what? No, it's the fucking sun.
Yeah, that's correct. That
There's
is crazy.
some characteristic of this that makes these pulses last about 11 months in duration. It's some characteristic of the magnetic field, probably, or the internal conditions on the sun. That period actually has shifted slightly in cycle 25. It's a little bit shorter. It's like 9 months.
Okay.
So anyway, it's kind of interesting. It goes back to your viewers talk about there's these things called Rieger periodicities
Hmm.
that people studied in the 80s and 90s.
Okay.
And they can go, there's screeds of literature on that stuff, but it's all tied to the same thing. And it's tied to Earth and the Rossby wave, right?
Yeah.
One of the things we noticed was that the bright points also pulsate, right? Because if they're tied to emission, if they're tied to magnetic field coming through the surface, of course the number's going to like give and take. And these are huge meandering waves that go in longitude around the sun. So that means that, there's a high pressure front and a low pressure front. And
That's
maybe, right,
like
at the
you can
interface.
see it really well when it's animated.
Yeah.
Like, yeah.
See that? So that's the bright point density. So this is a static. This is actually me scanning through different longitudes, right? And you can actually see the things slowly moving, right? So they're
Yeah.
going a little bit faster than the rotational period, which means that when I take a slice through this thing, it makes a straight line.
That's crazy.
So the things on the right-hand side are actually called hovmuller diagrams. That's a typo,
Yes, it
right?
is.
It's a typo, and those are diagnostics used to measure the speed of global scale waves in the terrestrial atmosphere,
Mhm.
right? Because that helps them predict where weather patterns are going to be N days later. Weather patterns? Fuck. So the sun has weather patterns and it gives rise to storms that live off the weather patterns? No.
No way.
I thought it was flat. Anyway, so you could tell I was having a lot of fun with this, right?
Yeah,
So,
I could tell.
and I didn't swear once. It was kind of cool.
No way. I don't believe that.
No, I totally didn't swear once. Right. I was very well behaved. I actually had to give the keynote talk. This is like the keynote lecture. So I just got off the plane about 6 hours before. So I was jet lagged and very well behaved. So, but I was having a bit of fun with this because there was some people in the audience that should know better,
Yeah.
right? And so the idea, of course, the analogy is here, the sun has weather.
Hmm.
Sun has magnetic weather, but has magnetic weather across timescales, just like we do.
Right. Yeah.
Right? Shock. Anyway, all right. So we've covered point one. Point two is kind of interesting. Most people don't know this one. And
Hmm.
in fact, the thing that Tanya and I have been talking about was the fact that even when we have X-class flares now, does that necessarily mean that we're in a surge?
Okay. Yeah.
Right? So this old previous analysis would tell you when we see one X flare, we should expect more.
Hmm.
This is that old adage that I like to use is the best way of predicting an X flare is one already happened.
Yes. I've heard that before.
And actually it looks like yes. So are we in a surge when we get X-class flares? The answer is probably yes.
Okay.
Right? So the fact that we get an X-class flare, does that tell you that we should be anticipating an increase in sunspot number or something? Maybe, maybe not. We're still kind of working on the diagnostics. Probably yes. But anyway, it's something that nobody really looks at because nobody looks at the sun as a system.
Right. Yeah.
Right? They love to break it down into stamp collecting because it's too hard to think about as a system. Anyway, whatever. Anyway, so you've got this mad global instability that's going on, which is driven by Rossby waves in the deep interior, which surge, which rotate longitudinally. And because they are rotationally driven buoyancy waves, there's that word buoyancy again.
Yeah.
You get longitudinal patches of increased pressure, which means that you would get longitudinal spikes in flux emergence, which means that you would get regions that emerge at the same place time and time and time again.
Okay. Yeah. Okay.
Do we see that?
Yeah. Yep. We do.
In fact, we see coronal holes that do that too.
Uh-huh.
Hmm. Wonder what population of coronal holes belong to the same process. Well, be careful. All right. Yeah, this is heresy tube. I don't know. All right.
That's too funny.
So, then you get to talk about forecasting. So here's an insert, right? So this is a plot I made for our most recent paper, just trying to illustrate the fact that you have this decadal scale mode, and then sitting on top of it, you've got this higher frequency thing, right? This isn't like rocket science, really isn't. But the higher frequency thing's completely ignored, right?
Hmm.
Let's zoom in a bit. Here's a cool plot. So this plot actually is very old, right? I call this the killer plot. This won a couple of proposals, this one,
Okay.
right?
Yep.
So it looks really complicated, but it's really not. Okay. Magnetic butterfly diagram in the bottom. So this is the daily magnetogram at 00 hours, at Zulu hours, and I just take a sliver of 5 degrees around the equator,
Hmm.
and then I do it every freaking day, right?
That takes some time.
Yeah, it takes a while to build this up, right? But you can see in this, so you see the red and blue, so the red and blue is polarity, but you see the very strong correspondence between the bottom plot and the bright points in the top plot,
Hmm.
right? So this is the extended wings. It has surges of emergence, right? You want to guess can you see the contours?
Yeah, a little bit.
Yeah, okay, there you go. This will help.
Yeah.
All right, so C class was blue. Nope, C class is green, M class is blue, X class is red.
Uh-huh.
And so whenever you get inside one of these tight contours, you get flaring activity, right?
Yeah. Yep. Look at that.
Here you go. When you just look at the number of C-class flares as a function of time and you plot all these surges, guess when they occur, when the X-class flares occur,
Right in
right?
those.
Red is northern hemisphere, blue is southern hemisphere. What is it?
That's pretty crazy.
You just slap them on the sunspot number. Look at that.
Yeah.
You don't get many when the sunspot number's at the bottom. You only get them when it's at the top, if you know what I mean.
Hmm.
Interesting, but nobody gives a shit.
Yeah.
Okay. So anyway, here's the bit that's kind of interesting that talks about the end of times, right? What happens when we get to the tail end of cycles? And maybe it gives a hint as to what the hell was going on in 1989.
Hmm.
Okay. So this is from an even older paper, right? This is kind of cool. So here's our bandogram thing again, right?
Yep.
This was done in 2014. So everything beyond that vertical dashed dotted line there is fucking make believe.
That was like the whatever the prediction was.
Except that it's right.
Yeah.
Okay. Now, here's a paper from 1992. And what they were looking for, and so Karen Harvey's a fucking genius, right? I don't know if you've heard of Karen Harvey, but she was like a mega star at the National Solar Observatory that unfortunately was taken from us way too early,
Oh, a
right?
bummer. Yeah.
And but she was amazing at analyzing data. And because they didn't have the volume of data that we have now,
Hmm.
they used to analyze every image. They would apply 15 different diagnostics to every image, right? Because they didn't have 10,000 images a day, right?
Right. Yeah.
And so this is a pretty simple plot, right? So it has crosses and circles. That's all. And the crosses are sunspots that obey the Hale polarity law.
Okay.
Little active regions. So it's negative, positive
Hmm.
in one hemisphere and flip the other way. And then the crosses are the ones that don't fucking behave. You know see where the circles are and where the crosses are,
Yeah.
right? The circles are on the periphery of the butterfly.
Yep.
Okay. And then you get these really weird ones. You get these times where there's lots of circles near the equator. Like, what the fuck?
Yeah.
Okay. And then you get them, they go all across the equator. This is a mess, unless it's not a mess, right?
Hmm.
So, shock the whole, you don't have to be a rocket scientist to go back and put your Hale cycle diagram on that old plot, right?
Right. Right.
And it's kind of interesting that those circles fall at the intersections, right? The circles fall in between. Does that mean that one band is talking to the other band? Or is magnetic field from one system emerging into the other one?
Yeah. That's pretty
So
neat.
you've got So what happens if you've got a Hale cycle obeying piece of magnetic field, and then something herniates into it, which is the other polarity? Tanya,
Tanya.
catastrophic breakdown.
Yeah,
That's called a delta spot,
right.
right? And the fact is that 5% of all the sunspots have 100% of all the drama,
Yeah, yeah.
right? This is another poorly understood thing, right? Like the bulk of them you couldn't give a shit about, but there's 5% of them that really caused all the trouble, right? But what's the pattern? Can you actually differentiate some of these things? So we were messing around with a lot of this stuff, and of course, there's these interaction zones,
Mm-hmm.
right? Where we think what we're basically saying is that these within a certain latitudinal separation, these bands all know about. Remember those arrows earlier that were saying, well, this one knows about that one and that one knows about this one?
Yeah, yeah.
They're talking to one another. But that means that part of that talking means that field can lapse from one system into the other system. And when you do that, you can create really complex things. And really complex things don't want to be complex.
They don't.
No, they really don't.
No. I don't like
They
it.
they want to simplify way the fuck fast, right?
Yes.
So here's another fun look, right? And yes, those are my hands. Here's the other bit that's kind of cool. And this is maybe why we get these really powerful storms at the end of cycles,
Okay.
right? Because there's this other thing that the rotation does. It creates left-handed things and right-handed things,
Okay.
right? So the Coriolis force, so in the northern hemisphere, the twists of the magnetic field is right-handed. In the southern hemisphere, it's left-handed.
Okay,
And
yeah.
and when those two things meet one another, wow,
Yeah.
it's so bad when it's two right-handed things or two left-handed things. But when it's a left-handed thing and a right-handed thing from one system into the other system, whoa, fucking
Yeah.
hell. Right,
Right.
right. And so there's so now you've got to play a mental game. You get a you've got the decadal mode coming in. You've got oppositely signed polarities. You've got different helicities, and on top of that, you've got Rossby modes, right?
That's a whole lot of stuff going on.
But it's all to do with pressure.
Yeah.
So it's all about the balance of pressure, right? And so what happens is you get these places in time, space and time when you would anticipate that these conditions exist. So like these green conditions here are places where you might get rapid energy release, right?
Yeah.
It can happen at mid latitudes too, but it's not quite as bad because you don't have this, you don't have the handedness problem.
Mhm.
You do have, you can make delta spots at high latitudes because one, I mean, so in the next few years, for example, for us, we'll see cycle 26 interfering with cycle 25, and you'll get some weird, where the hell did that delta spot just appear out of the blue at the edge of the butterfly diagram?
Right.
What's piece of cycle 26 interfering with cycle 25? Right? Nothing more, nothing less. And then, of course, as we get later in the cycle, we may have these cross hemispheric bad boys,
Hmm.
right? Anyway, so just because I teased it, I'm not going to go through all this shit.
Yep.
But just because I teased it, I'm going to leave it up there for a second for anyone that's dumb enough to read it. But I thought I would have a wee bit of fun with coronal holes,
Yeah. Yeah. Because
right? Because one of the things we talk about are coronal holes. And so here's, again, the Hale cycle bandogram from 1960 to the current, right? So again, this is my cartoon based on observations. And if I put if someone that's not me tracks all the coronal holes from say 1973 to 2008 and creates a public archive of them, and I can go in and rate them, and I plot the locations of the central latitude and longitude of those coronal holes for each Carrington rotation, this is what I get.
Huh.
So would you argue that coronal holes actually form a part of the Hale cycle?
Yeah.
It's a mess. But
Hmm.
we can see the polar coronal holes, right? So the
Yeah.
polar coronal holes match the underlying polarity. That's no big shock. But you see these long-lived coronal holes that start to march. You see them especially at the very starts of cycles. So and by that I mean solar max,
Yeah. Yeah.
right? You'll get these 55-degree-ish coronal holes that want to linger for many, many, many rotations.
Hmm.
Sorry, can I squint more? Right?
Yeah.
This familiar, right? And of course, if you add EIT, you get, you get another 20 plus years. So just for shits and giggles, let's do that. It's a better data source than where and I'm not the McIntosh in the McIntosh record, by the way. That's Pat McIntosh,
Right.
right? No relative, right? But you can see if you add EIT, it's consistent with the Macintosh archive, but expands it more because now instead of it being Carrington rotations, it's daily,
Right. Yeah.
right? So you get daily observations. Now you can start to see actually places where it's definitely fall. So this hasn't been what I would call disambiguated.
Hmm.
So this has short-lived and long-lived coronal holes in it, right?
Yeah.
Actually, one of the last things I wanted to do when I was at NCAR was have a hackathon and actually manually go through the coronal hole record and give them numbers. Manually say, yes, that's the same coronal, this rotation as that rotation,
Okay. Yeah. Yeah.
and then see how many rotations they live for, and start to parse apart the short-lived ones, which come from the decay of active regions, and the long-lived ones that follow the extended solar cycle.
That would be cool.
And then you can disambiguate this whole damn thing. Because of course, when you add when you add AIA, you get this,
Hmm.
right? So right up to the coronal holes that we're seeing at like 55 degrees are cycle 26,
That's pretty cool.
right? So
Yeah.
you're seeing these, you can see these tendrils of this red thing here, right? Right at the end of the timeline in the southern hemisphere, and a blue thing in the northern hemisphere. And if you look at these long-lived coronal holes that have been going around for 9, 10 months now,
Mhm.
that seriously don't go above 55 degrees. What the fuck?
That
Like a hard edge. Like I can't go there. It's like the forbidden forest, right?
it is funny. It's like, no.
No, like
Yeah.
my phone says no. It's like that Megan Trainor song that my kids play all the time that I hate. Right? My number said no, right? Yeah, that one. So anyway, I mean, so but the other thing that's kind of cool that I didn't show, I don't think it was on any of the slides, the coronal holes also do the whoa, right?
Yeah.
They also have this Rossby mode. So even the high latitude weak magnetic fields that become the next cycle undergo flux emergence. So the number of coronal holes at high latitudes ebbs and wanes. Same as I haven't really studied the correspondence between the two, but they definitely they exhibit exactly the same periodicities. So anyway, it's kind of cool.
Yeah, it is
It's
pretty cool.
a bit of a mess, but like what I'm trying to illustrate, I made it,
I
um,
it-
is that cycles, seasons, and storms are all wrapped up in one process.
Yeah.
And to artificially disentangle a flare from the mothership is a bit fake. It's extremely hard to, right? So going one way, it's easy, right? I can go from cycle to Rossby wave to individual event-ish,
Hmm.
but I can't go backwards. I can't go the other way, right?
Yeah.
So anyway, I don't know. I'm just rambling now, but it, it's kind of fascinating that we as a discipline break. We don't study what in meteorological terms they would call this seamless, right?
Mhm.
So you look at across the timescales and understand the system as it performs across timescales. But we want to do everything as stamp collecting. So it's like, oh yeah, my old PhD advisor, rest his soul, is gone now, but he used to say avoid any paper with a date in the title,
Okay, yeah. Yeah.
because very seldom will they try to tie it to anything bigger where you can actually kind of understand what the fuck's going on, right? And at the micro scale, there's so many weird little things going on that contribute to a flare, right? Especially a big flare. I mean, it could be absolutely minuscule. I used to call it kerplunk, right? Remember that game?
I do.
Just
It's
pop
yeah.
one straw and the whole thing catastrophically breaks down. Back in the early days of my uh, postdoc life, I studied these things called avalanches, and it was a simple statistical way of describing the flaring process. Like the magnetic field would become self-organized critical, and all it takes is one little thing here, and the whole thing cascades, breaks down.
Uh-huh.
So anyway, so in at some level, that's all tied to this stuff, and then there's what we're seeing now with the polar coronal hole or the not so polar coronal hole
Hmm.
is something we got to keep tracking. That is cycle 26, like it or not.
I like
No, um, it's tracking exactly where it needs to be.
like
Anyway,
imagine that.
um, totally mental, right? So anyway, I hope that made some sense.
Yeah, it's neat, like you said. It's interesting how compartmentalized everything went when it's actually like
Ooh,
a
yeah,
system that
yeah.
works. And I wonder if meteorology was like that, like, 50 years ago, if it was treated the same way. It's like instead of looking at a system as a whole, they were looking at little segments and they're like, hey, this actually affects this and this and this. Because it seems
Oh,
like
no,
this field is following what meteorology was like 50 years ago.
it's exactly. So meteorology before the space age,
Mhm.
meteorology was all local.
Right, yeah.
And so it was all you could see beyond your own horizon, right? And so this is why the National Weather Service has all these offices, right?
Makes sense, yeah.
Right? Because they would basically analyze the area around them, around their horizon, and they'd have like sondes and all kinds of things. And they would stitch their piece together and then they'd send it to like the next office.
Yeah.
Right? And the people at the top would kind of stitch all these things together into a global map, right? So it's interesting if you go back and look at it, it's a long time before that, but if you go back to the D-Day invasions,
Hmm.
and what the meteorologists were doing in the build up to D-Day is exactly this. They're taking all this local information and trying to stitch it into a global picture. Well, in the dawn of the space age, satellites were launched.
Right,
And
yeah.
and one of the first satellites was a thing that looked down. I think it was called Terra.
That sounds right. Yeah.
I can't remember what it was called, but it basically had a camera, and it's the same camera that Rossby analyzed the data from it and decided that there was these global scale wave patterns. So you know, like the hovmuller diagrams. You can go back and follow the literatures in the late 60s. And he started to analyze because he was sequentially analyzing these things and just taking them at the central meridian. It was like, well, that looks like a wave,
Yeah.
right? And so they diagnosed that it was a wave long before they figured out the theory of what these things were. And he noticed that they were like correlated with storm fronts, right?
Mhm. Yeah.
So rotating object with an atmosphere has global scale waves that are to do with rotation and buoyancy.
Yeah.
Hmm.
Hmm. Hmm.
Truly distinct in the whole solar system, right?
Yeah.
No,
Apparently not.
apparently not. But the thing that changed the game was the ability to look down on the
Yeah,
system.
that's true. Yep. You actually get to
So
see it.
you actually get to see the global scale. You couldn't see it from Galveston, right? Not until the hurricane's sitting right off
Yes. Yep.
right?
For sure.
But if you'd goes at that time, you could have told what was going to get the fuck out of here,
Yeah.
right?
Like, leave.
Yeah, run away, right? And but so many analogies, but it's the top down look. But I argue now that this is what I've been advocating for 10 years, right? So sure, I'm interested in the poles, especially 55 degrees. Did I say that?
Yeah, a few times.
But the only one time in human history that we've been able to see all of the sun was from May of 2010 to May, August of 2013.
Okay.
2014, sorry.
Mhm.
So you had SDO stereo, and you had the stereo satellites,
Oh, okay. Yep.
right? So you have SDO and EIT and SOHO on the Sun Earth line.
Hmm.
The stereo A and B, 120 degrees away.
Yeah, yep.
And so you could see the whole sun. And that's how we found the Rossby waves, right?
Yeah.
Because we took this global perspective, right? It turns out those are intrinsically important to understanding the scale that lives below them, the weather scale, right?
Yeah.
So maybe in my lifetime, maybe
Hmm.
we'll have a solar observing system that allows us to do this just like the weather guys have.
Yeah, that seems like that would be very helpful.
Yeah, but amazingly,
Yeah.
it's really hard to justify.
Yeah, which is this that part amuses me too because it's like so many people don't understand how important the space weather actually is until something really bad happens.
Well, and this is YouTube, right? So we've talked a lot about all the indicators for where shit things can happen.
Hmm.
If you have a global perspective, you can figure out where all the shit things are going to happen. You can actually see them before they happen, right?
Right.
And and I think Vigil is going to help because it's going to be at L5, and so it gives us a couple of days. Still not going to help with understanding the global puzzle,
Right. Yeah.
right?
Yeah.
Because a lot can happen between some going off the west limb and appearing two-thirds of the disk on the other side.
Yeah.
A lot can change, right?
Sure.
I mean,
Absolutely.
in cycle 25, that usually means huge flares going the wrong way,
Yeah.
or just as they go across the limb, right? It's only limb shots.
Yeah.
So, poor planet that lives over there.
Yeah.
Like,
Yeah. That right.
fine.
They've been blasted a few times.
But that in itself is a kind of interesting thing that
Yeah, it
it's
is. Yeah.
but the problem is statistically, this is the other problem. Statistically, you can't analyze that,
Hmm.
right? You can't see if there's an active longitude because it's obscured.
Okay.
The record, I used to call it goldfish mode, right? Well, yeah, let's call it a different fucking number. I think when we should call it one number on its first pass, and then when it comes back, I think we should call it a different fucking number.
Yeah.
Uh, let's do that. Let's confuse those poor minions, right? So you don't know the evolution of a active region
Hmm.
in the lifetime from the time that it emerges to the time that it decays. Are there ramps when you would expect more flaring activity or not? But we can't really tell. Intuition would say yes, but
Right.
because we get no observations, we can't say for sure.
Right.
And do you know that the two stereo satellites were meant to have magnetographs on them?
Oh, were they?
Those get descoped.
Oh, go figure.
Mm-hmm. That was a cost-saving exercise.
You know.
I mean, but also, I mean, so Ulysses back in the 80s
Hmm.
was meant to have an imaging partner,
Oh, see, that
right?
would
There
have been cool.
was
Yeah.
meant to be two satellites,
Hmm.
and they budget like I think well, Ulysses got launched on the space shuttle, and I can't remember the second one ran into funding issues, and had it not, we would have had images right over the pole of the sun like
Yeah,
15 years.
because it went over the
We would have
pole.
had polar images of the sun like 15, 20 years ago,
See that? That's a bummer. That's a big bummer.
right?
Yeah.
So all this shit that we're talking about here would have been solved a long ago.
Yeah.
And that's the problem is that like we still have this perspective that the sun's flat. And if you want to believe that the sun's flat, then all the other stars are flat too, because wanna bet me they all do the same thing.
I would put money on that.
Hmm. I actually think it could be really cool if you've got a really, really fast rotator like Jupiter, for
Mhm.
example, where you would actually have more bands per hemisphere than two.
Okay, yeah.
You could have outrageous number of bands if the thing spun fast enough. And
That's
then
great.
if they're all magnetically interacting with one another, you could have all kinds of fun,
All
right? I
sorts
mean,
of
I would think
chaos.
if I was a theorist, a theoretical astrophysicist, I'd have a fucking field day with that.
Right?
Take up so much shit you can't be verified.
Maybe that's what I should have took up to be.
I think
A
that
theoretical astrophysicist.
that's the real niche, right?
Yeah,
You got to
right.
make shit that can't be verified. So,
Oh,
now,
fun.
I need to go hit the beer fridge, but
Yeah. No, I had one question. It was like,
yeah.
does helioseismology provide much in a way of forecasting events? Because we do have
Oh, no. So if you go back and read documents for the helioseismic and magnetic imager, or HMI,
okay.
the entire that's really cruel. A large part of the science portfolio of SDO was sold on the fact that HMI could see magnetic field emerging before it pierces the surface.
Okay.
So if you can detect where magnetic field's going to emerge, maybe you have a shot at when it triggers, right?
Yeah.
Or you can see how that emerging flux destabilizes all the other stuff around it.
Mhm.
Doesn't work.
Oh, okay. Well,
We could spend a whole other hour on why it doesn't work,
yeah.
and why the people that pursue that thing don't change.
Mhm.
That's a whole different story.
Well,
But in principle, yes. But the problem
yeah.
is the big problem with helioseismology is that it assumes that there's no magnetic fields.
Oh, yeah. That's a problem.
The underlying assumption is there are no magnetic fields.
And when and when you're dealing with a magnetic thing, yeah, that could be a problem. A big one.
Well, you assume that it's hydrodynamic, it's not
Yeah.
magnetohydrodynamic.
Mhm.
And then all the perturbations you see are to do with the magnetic field, yet you don't go back and change the theory?
Yeah.
Hmm.
Okay.
And then I wonder why they can't make any progress anymore.
Right.
I mean, I'm trivializing it. That's not straightforward, right?
Mhm. Yeah.
But the fact that it gets swept under I gave that talk at a meeting 7 or 8 years ago.
Okay.
It was actually something we were going to pursue at HAO, was to do, we called it helioseismology 2.0, right? And the whole idea was, so we're going to relax the theory now to incorporate magnetic field,
Hmm.
and then try to use, AI wasn't around at that time, but we were actually trying to see if the magnetic field could be detected in different ways.
Okay.
Right. So if you could actually figure out, so take away all the hydrodynamic stuff and just isolate the magnetic signature of because it's all to do with waves, right?
Yeah.
So if you can take away all the hydrodynamic ones and just leave the modified hydrodynamic waves, which are magnetic, it's
Got
not
it.
easy.
Yeah.
But the idea is like, well, we've got 30 fucking years of data.
True. Yeah.
Right? I mean, you're not necessarily looking to do it on a day-to-day basis. You want to look over the whole damn thing
Hmm.
and see if you can, because clearly the magnetic field is impacting the wave signature.
Right. Yeah.
But yeah, I don't know. It's really complicated. But so the very long answer to your question is yes.
Okay.
All right. In principle, yes,
Yeah, in principle, yes, but
but it doesn't work.
yeah, it needs further modification.
Yeah, probably about 20 years of theory.
Yeah. Okay.
Yeah.
That answers that one.
Yeah. That was a very long answer to a simple question. Sorry.
It's okay. But I think
But
that's really the biggest question that we had.
all
So
right, cool. Well, hopefully that made a little bit of sense.
yeah, it's cool. Like even me not being a scientist at all, like what I think is neat about these kind of talks, even if some of it's above my pay grade, so to speak, but there's always something you can pick out of it. Like for instance, the overarching theme that this is a big system that if
Hmm.
you know that affects everything. It's not like flares aren't this and the coronal holes are this. It's like it's all interacting.
Right.
And that's a really, really cool thing to see, especially in
But,
the graphs.
but that also gets you to a point where like chicken and egg, right? You're
Yeah.
like, you got yeah. I think we generally just need better observational diagnostics,
Hmm. Yeah.
right? I think probably most areas of science would say the same thing, right? In Tanya's world, I need better internal diagnostics,
Yeah.
right? And a lot of people don't understand that medicine is still a remote sensing science, right? Generally speaking.
Yeah.
And you can misinterpret what you see
Yeah.
rather easily,
Yeah. Yep.
right? And it's right fucking there.
Right. Yeah.
It's not 93 million fucking miles away.
Yeah. Right.
Right? Which makes it even harder, right? So
Yeah.
but it's the same thing. I mean, I remember having a long chat with a doctor because I pondered going into imaging. I was in medical imaging for a while.
Okay.
I almost went down that path and I ended up in astrophysics. Another long story. But um we had this long chat about remote sensing. Like and I'm like, because it's funny because I used a lot of the same techniques that I used in geophysics when I
Hmm.
started because I started doing kind of geophysics, helioseismology kind of stuff back
Yeah.
in the early 90s when I was started doing my PhD. So, because I was learning the techniques, I ended up using those techniques for something completely different. But I went back and read all the seminal papers in helioseismology and redid all the theory
Yeah.
just to so that I fucking could, right?
That's
So,
cool. Yeah.
but anyway, so yeah, we need better diagnostics. Tell me a scientist that doesn't say that.
I'm finding that out right now. Especially as I get more acquainted with other scientists. It's like, yeah, we need better
Yeah,
stuff.
remote sensing is really tough.
Yeah.
And it's even more really tough when you don't have a lot of photons or a
Right.
lot of
Yeah.
particles, which is why the auroral problem's tough,
Yeah. That's
right?
true.
Even if you're looking down on it, we tried to get something on the space station
Hmm.
that looked at polarization. Um, and so polarization is how you measure magnetic fields, right?
Yeah.
So if you put something up there and you looked at the lights that are produced in the aurora, but you look at the polarization of them,
Mhm.
can you then measure the induced magnetic fields or the induced currents,
Okay.
which you then put into a model
Yeah.
to see, okay, well, you can actually measure it. Does the model actually correlate with the magnetic fields that are the currents that are being induced? Do they actually match up from the observations? We never get a chance to build that instrument because
Yeah.
the problem is that the things are so damn faint.
Yeah.
And like when you build a polarimeter to measure the polarization, it only uses 1,000th of the light,
That's not
right?
much.
So every
Yeah.
time you go down, you every time you chop the light, you go down like by 10,
Yeah.
10, 100,000, like fuck,
Yeah.
right? You have to build this huge fucking telescope, right? To be able to capture all that light. I mean, I still think probably somebody should look at it, but then you could actually try to correlate what we see from
Mhm.
above, from beneath, and in the middle,
Yeah, that would
and
be
see
really cool.
if any of it makes sense, right?
Yeah.
So because at this point, I'm not even sure we really know if the currents that are being induced are real. I mean, they're real, but are the numbers being produced by the models actually borne out by the observations? I don't know.
Yeah. Good point.
So anyway, that was another. Avenue. So, meanwhile, the sun's
Say
setting
something else.
behind you.
I know. Speaking of the sun,
Yeah, there you go. That it's flat.
yeah, it's flat. You know, I mean, it kind of goes along with the people of the internet crowd that still believes the Earth's flat.
Guys, of course the sun's flat too.
Of
And
course, the
all this
sun's
stuff.
flat.
Guy. Yep.
It's the only way it would make sense.
Yeah. No, I'm a full proponent of that. Let that be said.
Yeah,
Flat. Yeah, because it just goes off that side and then it pops back up and you give it a new number.
I know. So yeah, it's flat.
Yes. Yeah. Yeah. It's a big conspiracy, so we don't understand it. That's probably what it is.
Yeah, that's what I'm thinking.
Yeah.
I think, yeah, I mean, I think that was really kind of it. I don't know.
All right. Well,
Tanya, do
thank
you
you.
have anything to add? I'll call her back on real quick. Tanya, Tanya,
Tanya.
Tanya.
There is a little bit of a discussion in what models are and how they work compared to reality.
Oh,
Yeah.
damn.
Yeah.
Yeah, oh, damn.
Oh, damn.
Because that is a thing, especially in the aurora chasing world. Like a lot of people take models as fact. And
Yeah.
Yeah,
yeah,
it's all about assumptions, limitations, and uncertainties.
yeah,
That
Yeah.
and
And
taking in that all models are wrong, but some are useful. Really, it's at the core of looking at most models. And we may understand what data means, we may not fully understand the pattern behind that data. So it's like
and
we see data, we know it's there, we know there is a process behind it, but we may not be able to model it um, to really explain all the data. Something that's an outlier, particularly if it's a repeating outlier, there is a pattern behind it. We just
yeah,
can't figure it out yet.
right.
two things to remember. Crap in, crap out.
Yes.
And
Yep.
the second one is the underlying assumptions that are made going into the model determine the outcomes.
Hmm.
But very few modelers discuss the assumptions that they make.
Okay, yeah.
Right? So, like helioseismology, did you know that the fundamental assumption was that there is no magnetic fields?
Yeah. Which is just wild.
Look at that. Good for you. They don't advertise that,
Mhm.
right? They don't advertise that, then they find magnetic fields. Well, fuck me,
Right.
right?
Like,
Hold on, my brain's about to melt, right?
yeah.
And yeah, no, models are great if you understand the limitations. But
Yeah.
your point's absolutely right, Tanya. Is like you can go into it with they're all wrong, but they can be helpful.
Hmm.
Because really all it is an abstraction, right? All of this is an abstraction. Mathematics is an abstraction from nature, right? It's just a language that we use to express stuff,
Yeah.
right? And physics is another language that we use to express what we see, right? It's not exact. It's pretty
Yeah.
damn good, right? But this is part of the problem is there's no settled science, right? There's by definition there can't be,
True.
right?
Yeah.
So anyway, I'm very open-minded. I did a lot of modeling. Did a lot of modeling when I was a young postdoc, and it was brilliant. Loved it. Brilliant stuff. Not on this global scale stuff. It was all to do with the waves, actually, believe it or not.
Oh, that's
So
kind of cool.
small scale stuff. So, but I love that work. A lot of cool things you can figure out about acoustic waves and magnetic fields and things like that.
Mhm.
So anyway, so
Neat.
thank you for your
Yes.
persistence, Tanya. Thank you for your persistence.
Yeah. Thank you
No,
for
thank
coming
you.
on.
I do appreciate you guys very much, and especially on our Discord that you guys aren't on there so often, but you make phenomenal contributions when you do. I haven't been on
Yeah.
there in weeks, it feels like. So
Yeah,
uh,
it's fun. I like it. It's a fun, lively discussion a lot of times, and so it's always cool to chime in there here and there.
it
You know,
doesn't go
us lowly aurora chasers.
please, it's amazing. Practical reality is a huge thing, right?
Yeah.
It's
Yep.
for me who's deals with a lot of abstract stuff,
Hmm.
it's really awesome to try and understand things that are practical and then practically useful too, right?
Yep.
Because I look at the applications of the work that you guys do as amateurs is phenomenal. And your insight into substorms, I get lectures from all kinds of people on this stuff, right? And it's like,
Yeah.
but that's not where the academic world lives. The
Right.
academic world is still in spherical cow mode, right? Like they're not like, and so this is the part of the problem with the auroral prediction models, right?
Right. Yeah. It
They're
very much
very
is.
much in spherical cow mode and not in, and there are in the street practitioners that are 1,000 times better at that than the modelers are.
I know, isn't that's kind of crazy, but
Because,
as I
because
think Tamitha says she likes to sometimes bring this in too because it's like it's because her frustration with is like what you're talking with academics is like you're kind of stuck, and then us people that are on the outside are free to kind of explore things because we're not tied to these different rules.
well, the paradigms, right?
Yeah.
Yeah, the paradigms are very strong. The dogma
Yes.
is
Yeah.
very strong,
That's a good way
right?
to put
It's
it.
like the stuff that the non-dogmatic stuff that I was discussing for about,
Yes. Right.
that's why there's a problem with that.
hmm
Because it's completely orthogonal. This whole idea that magnetic fields know one another and
Right.
interact. Remember, there's no magnetic fields,
Right. Yeah. That's right. There's
right?
yeah.
This whole thing that these huge magnetic fields should feel one another, and then you get an event like the Terminator happens, and all of a sudden everything changes. Holy fuck!
Yeah.
How do you explain that?
Right.
Right? How do you explain that something that happens triggers a change in the entire magnetic environment, and it happens again and again and
Yeah.
again, and you can't explain it in the current paradigm. You can't do it.
Yeah.
You can't, because by definition, the models that are developed to do that work cannot have interactions in them.
Yeah. Yeah.
They
Which
cannot. They cannot. It's a fundamental binary thing, 0 and 1. Cannot. Right?
Hmm.
And this is the subtlety that people don't get. It's not really a subtlety, right?
right.
The magnetic fields are so passive that they just follow the flows. Whereas in our world, it seems like the magnetic fields dominate the flows,
Yeah.
right? And so you've got this very weird dichotomy, and well, who's winning right now? I don't know. Anyway,
Fascinating.
sun will kick it. Don't worry, the sun will just hang around long enough. The sun will kick it is all where it hurts.
Yes.
So
The sun.
the sun, and bless you, sun.
Yeah. Bless you. We love seeing you.
Yeah, I'm Scottish. I didn't see him for 25 years, so it's okay.
Right. Yeah.
I was aware of some faintness in the clouds, but other than
Yeah.
that,
Like it's theoretically there.
yeah, there's a slight lightning in the cloud up there.
Yeah.
It's
Anyway,
not doing much right now. It's throwing at best C-class flares, so kind of calm.
yeah, we're not. I don't know if we're in a surge. Like, I doubt it.
Mhm.
So anyway, watch out, watch the space. Great chatting with you guys, catching
Yes,
up again.
likewise. Thank you so much. We always love
And
having.
I'm sad that Christian couldn't be on,
Yeah.
and we'll catch up with him later.
Yeah, I'm sure he'll rewatch this, or he might actually be watching it. So from
Poor
work.
bugger.
Yeah. I know.
Poor bugger. All right,
Oh,
well,
well.
take
Yeah.
care, guys, and I'll talk to you
Yes.
soon. Okay?
Thank you so much.
Right. Thank you
Right.
so much.
Bye.
Goes.
Bye.
Bye.